Hello everyone. Today I will speak about Pixi and how Pixi bridged the world between Conda and PyPI in Rust. My name is Nikita. I started as a backend engineer, and with time I found my passion for the open source and for developer tools. So now I'm working at Prefix Dev. I want to start in a more interactive way my presentation, and I will ask you some questions. Are you sometimes reading a long README just to run the project? Maybe like this one. Are you sometimes switching the Python version, maybe using PyEnv because the project does not support your old or newer Python version? Have you faced the situation when your project is running fine, but the tests fail because of a very small mismatched dependency version? Everything is fine. We are all here, and all this kind of the situation can be expressed by using a more umbrella term like dependency hell, or it can also be visualized using this image. As we can see, a developer needs to have a homebrew, for example, like a system package manager that will install a Python. You also need to use maybe PyEnv or conda to install something else, and it all go in different directories. So it's very complicated, like in a developer day, to understand what is going wrong. So we know that all this stuff is very complex, but I think it will be nice to understand why and like why it's so complicated and why there are so many tools and standards. And we will go back in history for a little while and understand how package configuration evolved in Python world. So it started in 2000. People were using setup.py for configuration of your package. It was easy to do because like you will use Python to program your script and also use Python to program your package configuration. But it grew in complexity, and every project will have its own style of set.py. Someone will read the requirements from a file, others will use constants for that. So there was an idea in 2008 to have a setup config file, which will extract the metadata in a more declarative way. So you just need to type the name and description in that file, and setup.py will build it. And ultimately, it will be involved in 2016 when the PEP 621 arrived with the PyProject YAML. It was an innovative way to, and the standard de facto of declaring your package. And the cool feature is that in PyProject YAML, you can also specify what build tool will build your package. So basically, you can choose between setup tools, maybe Poetry or Hedge, which is very cool. And also, apart from configuration, the packages distribution also had some changes during the history. So initially, they all were distributed as source packages. This is very easy to do. Basically, your end user needs just to download the source, build it, and run it. But if you have some C extension maybe, or you're writing something more complex, your user or you as developer also need to have the build dependencies. So it's kind of complicated to distribute them also, or it's like the responsibility of your user to install them in the environment. So in 2004, Makefile appeared. It's a very historical format, and it was the first way to distribute built packages, but it has some problem. First one, that it wasn't strict specified what should go in the egg file, and it was also both distributable format and installable format, which is that under the hood created some edge cases. So in 2012, will appear. It was the first standard with a proper specification how you need to distribute your build Python project. And it also has a specification implementation that is also named will. So will currently is a standard de facto of distributing the Python packages. And also in 2012, conda appeared to fix the problem with more complex binaries distribution for libraries like NumPy. You know that it's sometimes complicated to install them, especially for Windows platforms that were kind of little supported. So now today you as a Python developer need to handle multiple buzzwords, like you need to know about source distribution, wheels, you need to decide what tool you will use to manage your virtual environment, maybe venv or virtualenv or pipenv. You need to take care about different build tools like Hedge or like what you will use to upload stuff. and you need to also know what your libraries or where it will be installed. Maybe it will go in a side package folder or maybe as a system library somewhere. So it's complicated. And we have a solution for this problem. Oops, sorry, this is the wrong slide. We have the solution for this problem. We think to escape dependency hell and to bridge the world between Conda and PyPI together. Meet Pixi. So I want to capture your attention and first to show what kind of projects Pixi can run. So this is a robotics example where we can see that Pixi can manage a C++ and spin up the user interface for you. This is a small example where I'm running the Whisper LLM. So I'm just doing a Pixi run and it do all the stuff for you and the transcription of my hello message for everyone. And this is my favorite example. So maybe you have some C++, like heavy C++ project. Pixi can bring you CMake Ninja and you can run Doom inside your terminal with just using the Pixi. It's very cool. I really like this example. It's my favorite one. So let's take a look about, let's make a small overview about Pixi. What is Pixi? So first of all, and the most important, is that Pixi is a cross-platform package manager. This means that it has first-class support for Windows, macOS, and Linux. Pixi is also language agnostic. While it's widely used for Python projects, you can manage different language projects, maybe C++ or Ruby. It also has a first-class support for Conda and PyPI packages. It offers you, as a developer, log files out of the box, and later we will see why are they important. And Pixi also has a very nice task system. You will have a more minimal and more developer-friendly workflow. Maybe imagine Cargo together with Makefile. It's also very easy to install Pixi. You just need to install a single binary. We are also a next evolution of Conda ecosystem, and we are blazingly fast. And our core philosophy for Pixi is that we sometimes say that Pixi is a missing Git companion. So we want that you as a developer or maybe your user just need to do a Git clone of the project and Pixi run a command, maybe Pixi run start, and Pixi will take care of installing all the libraries and all the dependencies that you have in an isolated environment and run that task. So basically you as a user don't need to know how to install stuff or reading the long readme file. You may ask why we are using Conda. There are 4 PowerPoints in my opinion. The first one, it has a great support for data science. It basically has a lot of libraries that supports Windows, so it's very easy to install them on your Windows platform. It's also great for machine learning. It has a lot of GPU accelerated packages that you can very easily install with Conda. It's also great fit for robotics because you can combine C++ and Python together. And it's also very nice for cloud or side deployment because you can run Conda packages everywhere. You can think about them like a very minimal Docker. We are also using CondaForge, which is a huge open source channel of packages. There are a lot of packages for Python, but not only. It also has a very, let's say, strict contribution workflow. So basically, before you contribute a package, it will be reviewed by CondaForge team or other contributors. So every recipe has a very good standard. It has some tests and linters. So yeah, and also CondaForge offer a very nice infrastructure. So we have some bots there that will keep your packages up to date for you. So it's very easy to use it. So let's see where Pixi fit in the Conda ecosystem. So initially in 2012, Conda were developed using Python. With time, a lot of package number grow up, so it became a little slower. And Mamba appeared in 2019. It was a C++ implementation of the Conda. And now, in 2023, we are re-implementing it in Rust. But I would like to say that Pixi is not just a simple package manager, it's also a workflow tool. And it can also be expressed with this diagram. So on the right side, we see Conda workflow. Conda workflow offers you a very nice environment workflow that you will activate maybe a base environment, switch in one project, will run something, maybe switch into another environment. But Pixi it's like let's say evolution of this, and we offer you a project-based environment. So you will just go in your Pixi project, we'll do a Pixi run, and it will create the environment and the log file for you. So it means that we don't touch your base environment, and every project will have its own isolated environment that you can easily remove and run Pixi run again, and it will spin up for you. So now let's take a small tour of Pixi. So for today, we will have 4 stops. We will take a look how you configure a Pixi project and what formats does it support. We will take a look at Pixi tasks, what they are and how you can write them or use them. We will take a look at log files and why they are important for you and why you would like to have them in your project. And we will also take a look how Pixi and like why it's so fast and how fast it is. So our first step is like looking at the Pixi configuration for the project. You can configure a Pixi project using Pixi-toml. This is a very minimal example of how it looks like in real life. You can see that we are using project table, and 2 features that I would like to highlight is channels and platforms. So channels is a field where you will say from where you want to get your packages. So basically, for example, in our scenario, we are using conda-based. Platforms, it will mean for you or your user what platforms your project supports. So in our case, we support OS X and Windows, and it means that if an user from Linux will try to run the project, it will receive a very nice error that this project does not support Linux, instead of guessing like why it doesn't work or why I cannot install it. Also, we have a tasks table. Here you will add your task for your project. We have just a very minimal one, hello world, that will run the Python and a script. And we have a dependency table. Here you will list all your dependencies that project need. For example, Python, Reach, or other libraries, and also PyPI. We also support PyProject.toml, so you will have a very familiar way of configuring it. So the only highlight that I would like to do is that requires Python field will be picked up automatically by Pixi and will install the Python in your isolated environment. So it's very handy and easy to maintain the Python versions just in one field. And other Pixi configuration, you will just put it under tool table, which is very familiar for you when you configure, for example, MyPy or PyTest. It exactly the same works for Pixi. So log files. After solving the dependencies, we create a log file in your project, and inside the log file, we record everything that we need to have in order to reproduce your environment again. This means that we take the URL from where did we get the package, what are the hashes for it, what are the dependencies inside of this package, where or what was the size for it. And you may ask, why do I need to have a log file coming from example having just a requirements.txt file? It basically to fix the problem that it worked on my machine. Usually you will have this situation when you are running something locally and it works, but in the CI it doesn't work anymore, and you are thinking like, I don't know, it worked on my machine. So the answer is that why do you need the log file is that you will solve only once. So let's say that you are starting a new project, you will list your dependencies, you will solve them only one for every platform, and you will receive the log file that you can commit in your Git repository and use it everywhere or anywhere. It means that your next developer will just git clone it and receive the entire log file without solving it again. This also gives you a very nice understanding of your environment, because basically log file is the source of truth what your project will install in your file system. So if you want to understand what have you installed, you just need to just take a look at the Pixi log file. And it fixed the problem that it works on my machine. Pixi tasks. So this is a more complex overview of what Pixi tasks are capable of. In our case, we will have a small task that is named download data that will download some CSV from URL. And we have an outputs field. This is very cool stuff because you can specify for Pixi what you want to cache after executing a task. So in our scenario, if we downloaded a CSV once, we will not run this task again because the output didn't change. And you also can specify the input of your task. So for train, we see that we are running a script, but we want to have an input for it. In our case is a some CSV file, and we will skip the task if the input didn't change from the previous run. And we also can depend on other tasks, which means that you can create kind of a graph workflow of the tasks. So the main one, the last from this example, we are running the main Py script only after we execute train and test, which is very easy like to do. So this is a very small example how it looks like in practice. You seen that it was very fast because we skipped the first two tasks like download data and the train task because they were cached and the input or output didn't change, and we just executed test py and main py. And it also, I would like to mention that when you are doing Pixi run, it will verify that your environment is not out of date. So basically it will take a look at the log file, it will take a look like what you have installed in your environment and run it. So it was like super fast here. So I'm always saying that it's like super fast, it's like blazingly fast, and I think you're curious like to take a look at the real numbers and like how fast we are comparing to other tools. So we will take a small environment and as example, usually like what libraries you will use for your project. Here we have matplotlib, seaborn, polars, and scipy and others. And this is the results of our benchmark. So you can see from the numbers that we are 10 times faster than Conda and 3 times faster than Micromamba. And here we have also a very small URL to our benchmark repository. So if you are curious to reproduce these numbers, you just need to do git clone and Pixi run start. It will start the benchmarking. It will install the hyperfile library, the Conda, the Micromamba, and will plot these results. So it's very easy to do with Pixi. And I think you are curious like how and why we are so fast, like what tricks we have done under the hood. And I will start with the first one. It's the core or the heart, like I would like to say, of every package manager. It's a SAT solver. So we implemented our own SAT solver in Rust. SAT solver is an algorithm that basically will say if your, let's say, Jinja and PyData packages are can be satisfied and can be installed together. So we implemented resolvo. It is very powerful SAT solver because it's first of all can be used in multi-threading environment, and it's also generic over other packages ecosystem. So you can implement it for, let's say, JavaScript ecosystem. And my favorite one is that it has a very nice human errors. So if you cannot install something, instead of guessing from the long red pip output, like what it doesn't work specifically maybe with Jinja, you can just take a look at the numbers, and Resolve will guide you like to understand what exactly, what version match specs doesn't work together, and it's like very easy to fix. Maybe in future, I hope we will also fix it for you, but now we give you just the human error message. We also have a faster PyPI integration. So initially we were working on RIP, which was a pip reimplementation in Rust, but UV appeared on the scene. So we needed to decide, do we adopt UV under the hood, or do we want to try to make the feature parity between RIP and UV? And we decided to adopt UV. And you may wonder like why. So apart from some technical complexities that you will have when you will work on a pip-like tools, so for example, during the solving of dependency, you need to build multiple source distribution and you need to do it very fast. You also will have some packages that will have a wrong archive layout, for example, or maybe wrong record files. The main thing is that we didn't want to divide the ecosystem between two tools. So our goal is to make the ecosystem better together. That's why we decided to adopt UV. So now that we have seen a small overview and a small tour of Pixi and how it works and what are the power features for it, I think you are curious like, how can I use it for my next scientific project? So I will show you a very small demo. Here I came up with a small MVP, let's say in this way. I want to use a ResNet model to detect something from an image and how you can do it with Pixi. So these are some base dependency of your project. We will bring Python, PyTorch, JupyterLab, or other libraries that you need to have in your project. And we will have a very, let's say, complex task system here, basically because if you want to use RESTnet, you need to download some image classes, to download some weights for it, and it's very easy to do and write with Pixi tasks. And the last one, the most important, is that when you will do some detection using RESTnet, Pixi will see that it depends on the download the image classes and the build on the build model task. We'll do it them first, and after that just do the Python detect. So this is very cool because you don't need to install, or you don't need to read the README or run some Makefile task. Pixi will do automatically for you and give you the result. We also can build the model using Pixi as a task, and you can use retrobuild, which is our Rust layer implementation of conda-based for building this model, and you can specify it as an environment feature and as a task. And maybe some of your developers have CUDA and they have GPU, or you want to have more accelerated package. You can also have a separate environment, let's say CUDA one, where you will say that you are bringing PyTorch CUDA from two channels. Maybe you want to bring it from NVIDIA or maybe from PyTorch. You can also have a private channels if you develop some more accelerated and you want to host it as a private. So now we will have two environments, the base one that will have just RESTnet, and the CUDA accelerated that your developers can run on Windows or Linux platform. And maybe after a while you want to do some research, or you want to do some experiments, and you need JupyterLab for it, but you don't want to add it in your base environment. You can specify another feature that will be research. You can list the dependency there. You will have a very nice and small task start that will spin up the JupyterLab. After, it will download the image classes and building the model. And the last step, let's say that you're finished with your researching, you want to host your model, you want to serve it, so you will need a web environment. You can have as a feature here where you will list the fast API, and maybe you want to bring a specific PyPI libraries. You will do it under PyPI dependencies. In our case, it's PyDating. So at the end, you will have multiple environments that Pixi will manage for you and install them automatically for you. Maybe you can take as a next step, you will have a test environment, you could have a linter environment, or maybe you can divide them between like dev, staging, prod. This is very easy to do with Pixi. You just need to list them under environments, and when running a specific task, Pixi will pick up it for you. And this is a very small demo how it looks in practice. So I am doing Pixi run start. It downloads all the stuff, it builds the model, and it will start the JupyterLab. I'm having an input image, and after that I'm running like the code that I need to run to detect something from an image. And it's all done in Pixi environment, in isolated environment, and I didn't have any dependencies prior running this, so it's very, very easy to do with Pixi. And your colleague or you just need to do git clone Pixi run start, and it automatically bring all the stuff that are necessary for you with Pixi. So instead of reading a very long README file, like installing a compiler, making a directory, switching into them, maybe you will create an isolated environment with venv, source activate, install it. You just run Pixi run, and it will be bring it for you. I really hope that I sparked your interest in trying Pixi, or maybe even trying Pixi for your next project. So you can download this binary, or you can bring me your laptop after the presentation, and we will do it together. Join us on GitHub and Discord. We host every 2 weeks a public show and tell, so you can see what we are making, like new stuff, and you can also give us your feedback. Thank you very much.
Thank you very much for a really nice talk. Any question? Okay, so 2 hands raised there. I'm gonna pass it first to Evelyn, and then you can pass it.
Thank you very much. A lot of exciting stuff. I was wondering, you at the beginning of the talk, you kept comparing Pixi with all of those tools that would help us create environments. But with Pixi, I didn't see any way that I would get an environment. Like I want to have an environment where I'm a developer, and I don't want to get a project and run. I want to run my PyTest. I want to have my Python interpreter. I want to experiment. How do I get that with Pixi?
It's a very good question. I can show you in more practice way. So if you want to have a PyTest dependency, maybe you will specify it as a separate environment and list it there. So basically, if you need to run the tests, you will do Pixi run PyTest, and it will spin up the isolated environment for you and run that PyTest inside of it.
So there's no way that I get a shell where I have control over the commands that I
You
run.
can also have it. You just do Pixi, I hope you can see it. You will do Pixi shell, and you will receive the your isolated environment in the shell itself.
Thank you.
What's the current state of affairs of WebAssembly in Pixi? There's something about on your blog post, but you did mention it in your slides.
Yeah, it's a very good question. I think this Friday we also host a public show and tell about Conda and WebAssembly. So we support WebAssembly. You can specify it as a platform and run your Pixi project using this platform, basically. We are using ECMAScript Forge to bring all the packages that work for WebAssembly.
Any other question? I'm gonna come to you.
Where does the name come from? What does Pixi mean?
It's a good question. I don't know really. But this is Paxton, our mascot. Yeah, it's his name.
Thank you for the presentation, very exciting. Maybe I just missed it. How do you, currently we have a list of dependencies, right? Dependencies, txt, dependency in dev. Can Pixi create somehow this configuration file on its own, or I have to do it manually?
Yeah, it's a very good question. I didn't mention it, unfortunately. You will do Pixi init to start your Pixi project automatically. It will create it. And you have a CLI to interact with it. So if you want to add a dependency, you do Pixi add Python. You can also import your old environment YAML with Pixi. You will do Pixi init with a specific flag, and you will specify the environment, and it will create the Pixi project for you. So you have entire CLI that will interact and automatically update and keep the log file up to date for you. You don't need to interact it manually. Yeah.
Last, yes?
What if you have an existing configuration environment, typically with a requirement.txt or a poetry by project toml, or does it work? Can you import it directly, or is there some troubleshooting to be done to migrate from one to another?
Yeah, it's a very good question. So poetry and requirements.txt, unfortunately, you will need to copy them manually, but you can configure Pixi using PyProject.toml. So you can just create a table there and just do add run Pixi init with the PyProject.toml, and it will create a table there, and all the dependencies that your PyProject.toml has, it will bring them as a PyPI, but you can also move them as a conda.
Thank you very much. Thank you very much.
Thank you very much.